Hello, everyone. We move on to study lecture 3 of module 4 in this course about robotics. In lecture 1 of module 4, we have studied 1 design technique in time domain and 4 design technique in frequency domain. And in lecture 1, we have exposed you to many basic concepts in control theory. Therefore, in subsequent lecture, so we will give you complementary knowledge about these basic concept in control theory. In particular, in today's lecture, so we will give you a quick study about the Laplace transform, about the transfer function, and the control block diagram. Then we apply the concept of a control block diagram to visualize the inner structure of a control for robotic arm. Therefore, you will have a better idea about the detail of system under control with regard to robotic arm. Before we enter the study of today's lecture, it is always good to remind you about the learning objective of this course. The learning objective of this course is for you to become a designer of a robot as a product. By now, you should know that the robot are motion provider, and in manufacturing and in society, there are many generalized users who may have this generalized need to have a motion provider. Therefore, robots are very good product for those buyers with the need of having motion provider. If you put yourself into the mindset of a designer, then your focus should be on the answer to question number 3 and the question number 4. For example, you may want to know what should be the blueprint of a robot to be designed by you or your team. Therefore, this slide gives you a general guideline. This slide basically shows you the signal flow and the energy flow inside your product, all right? And you can identify the presence of these 4 modules included in this course. For example, you see the module number 1 is here, module number 2 is here, now module number 4 is here. Then module number 3 is about the modeling of a robot in terms of kinematics and dynamics. Therefore, you see the presence of these 4 modules of this course in this generic blueprint of a robot. In order for you to drive out the detail of this blueprint, you need to have a good understanding about these topics, which has been categorized into this 4 modules. Therefore, after the study of module 1, you should be able to design software system for a robot. After the study of module 2, you should be able to design the body for your robot. Then after the study of module 3, you should be able to develop a simulator or simulation or digital twin of your robot, all right? Then now we are in the study of module 4. Then after the study of module 4, you should be able to design control system for your robot, right? So now we enter the study of lecture 3. So we will first go through the background knowledge about the Laplace transform, transfer function. Then you will see the benefit of a transfer function or benefit of using transfer function. The immediate benefit of using transfer function is to be able to visualize the inner structure of a control system in the form of a block diagram. Then we apply this concept to draft out the block diagram of robotic arm on the control. All right. Why do we need to use the Laplace transform? The first motivation is to simplify the solution to differential equation. So in lecture 2, so you remember the first section of lecture 2 show you the dynamics equation at the robot joint. Then you will see we have a differential equation. And in particular, for robotic arm, we have a derivatives equation in the form of a matrix. Therefore, to find the solution of a differential equation is a challenge to us. Then you will see if we undertake a Laplace transform, then we are able to simplify time domain function and transform a time domain function to become a polynomial equation in frequency domain. Okay, so this is the first motivation. Second motivation is to have this benefit of defining simple transfer function. Okay, then third benefit will be the application of a transfer function in order to graphically draw the inner structure of the system under control. So then you see all this benefit, then there is enough reason or motivation for us, okay, to adopt frequency domain mathematical tool, okay, in order to come out with design solution to robots control system. All right, so we start with a quick study about the Laplace transform. Mathematically, Laplace transform means these two integration. First, we do this type of integration with a time function. Then we obtain a function which depends on the variable s. Then here s is a vector. In the textbook, people say that s is a complex number. So I believe it will be more intuitive for you to understand the physical meaning of s. Actually, s is a vector, all right? Then the second integration is to take s function as an input. Then we do this type of integration. Then we can recover time function, all right? So fs is called as a frequency function. ft is a time function. So then here we have a forward transformation and the inverse transformation, all right? So the formal description of a Laplace transform is shown in this slide. So if we have a time function, if we undertake this integration, result will be frequency domain function. Then we call this as a Laplace transform of this time domain function. If we do this integration with Laplace transform, then we can recover the time domain function, which correspond to this Laplace transform. Then here, some of you may say, wow, this is very complicated to undertake these two types of integration. But the good news is, in practice, you will never use these two integration because you can apply some simple rule in order to find out the forward transformation, inverse transformation, all right? So this is just show you the rigor, mathematical rigor about the Laplace transform, just to show you this is a very, very powerful mathematical tool. But in practice, you have a very, very simple property for you to use. Then you will not, okay, be required to undertake these two type of integration, okay? So actually, Laplace transform gives you two integration. One is for forward transformation. So this diagram shows you if you have a time domain function, then you can obtain frequency domain function. Inversely, if you have a frequency domain function, then you can obtain time domain function, okay, through the integration. But in practice, you can apply the property of a Laplace transform in order to avoid using these two integration, okay? So before we look at the important property of a Laplace transform, let's pay attention to the physical meaning of a S, because in textbook, people always mention S is a complex number. So actually, when you see this technical term, you can never refer it to vector, because the concept of a vector is very important, because it will help you to understand a lot of things in control theory. So therefore, I prefer you to keep this concept in mind. S is a vector in this complex plane or in this two-dimensional space. Horizontal axis is a real number. Vertical axis is an imaginary number, because in front of this number, we have a j equal to square root -1, which does not exist in real life. This is why we call this value as an imaginary number, all right? So mathematically, you just treat it as a two-dimensional space. Therefore, S is a vector. This S has a two component, horizontal component, vertical component. J is the operator. Just now I mentioned it's like a square root -1, okay? So you just treat this as a vector representation for S. That's it, all right? Then how come people invent this J? So the answer is this is an invention by Euler. This is an Italian scientist. He has discovered or invented this equality. Then inside you see you have a J operator. J is equal to square root -1. Okay. So natural exponential function with the power, which is equal to j omega t, is equal to cosine omega t plus j sine omega t. This is a very beautiful equation in mathematics. All right. Then the French scientist Laplace use this result, then define S as a vector, which is equal to a real number plus j omega. Then use this vector to extend Fourier transform. Then he discovered this Laplace transform. All right. So these are the background knowledge for you to know. Okay. So keep in mind, treat S as a vector. Therefore, later on we will talk about transfer function. So transfer function is also a vector. All right. Once you have a vector, then we can talk about the magnitude. We can talk about the phase, angle. Okay. If you treat S as a complex number, then you will get confused. How come we talk about the magnitude, we talk about the phase, angle, etc. So actually, S is a vector. Transfer function is also a vector. All right. So now we look at the least useful property. First property is to reduce the complexity of derivatives in time domain into multiplication with S. For example, if X is a time function, we know the Laplace transform of X is XS. Therefore, the Laplace transform of derivatives of X is equal to S times XS. So it means when you encounter derivatives, change it to S in frequency domain, done already. If you have a second order derivatives, then in frequency domain, it becomes S squared. If you have a derivatives of order n, then in frequency domain, you have S with a power, which is equal to n. That's it. So you see, in frequency domain, the equation becomes extremely simple, all right? Another good news is about integration. When you have an integration in time domain, then in frequency domain, you just replace it by 1 over S, done already. So you see such a simplicity, all right? So you do not need to actually compute integration of a time function in order to obtain frequency domain function of Laplace transform, all right? Another simple property is about this natural exponential function. If you have a natural exponential function, like this. In Laplace, in frequency domain, the Laplace transform is equal to 1 over S plus A. So actually, so it means when you have a function, because you can treat this as a 1 times this one. So this could be treated as the 1 over S with S on the go horizontal shift, okay? Then, so because the inverse Laplace transform of 1 over S is equal to 1 in time domain. When S on the go a shift, then it means you just A in this exponential function raised to the power, which is equal to negative AT. So this is also a very, very popular rule, simple rule for us to apply in order to do the Laplace transform, okay? On top of that, if let's say you have a S with a power which is greater than 1, let's say 1 plus n. So this means in time domain, you have this term t raised to the power, which is equal to n, okay? Then all these simple rules, you can combine them together, all right? So here is an example. Here we apply 2 rules. First, S on the go a shift. Then it means what? In time domain, you have this term, exponential function raised to the power, AT. And you see this term has a power which is greater than 1 because it's 1 plus n. So it means in time domain, you have this term, t raised to the power n, all right? So you can combine this simple rule together. Another useful result is to reduce the complexity in time domain with the sine cosine function into the ratio between 2 polynomials, all right? For example, in time domain, sine omega t, it is quite complicated function, okay? But when you do Laplace transform in frequency domain, you see this is very simple one. It's a ratio between 2 polynomials, okay? For cosine omega t is the same in frequency domain, then you have a ratio between 2 polynomials. That's it, okay? So this gives you enough motivation for us to transform the complexity of the equation in time domain into simplicity of frequency function in simplicity of a polynomial equation in frequency domain, all right? And then here show you some example for you to apply the complex rule. For example, we have this transfer function with S on the go a shift. Then immediately, originally, this looks like a Laplace transform of a sine omega t. When there's a shift, okay, by vector S, then it means in time domain, we have a exponential function raised to the power, which is equal to negative AT. Then for this one is the same, okay? So in time domain, this looks like it's a cosine omega t. However, there's a shift by vector S. Therefore, we must A in this term, which is equal to natural exponential function raised to the power, which is equal to negative AT, all right? Then for the Laplace transform of some simple function, you just need to remember these 3. Then the rest should be, you should be able to come out by applying the rule. For example, for unit impulse function in time domain, then in frequency domain, you have 1. Unit step function in time domain, then in frequency domain, you have 1 over S. And the ramp function in time domain, then in frequency domain, you have A divided by S squared. A could be equal to 1, 2, 3. A is a scalar, all right? Okay. Then another useful result from Laplace transform is to estimate initial value of a time domain function without doing inverse Laplace transform. That means directly use function in frequency domain, then calculate in this way, then the result will be the initial value of a time function, okay? And another useful result is a final value theorem. This is more useful in control theory because we may want to know what is the steady state response of output, steady state response of error. So when you talk about steady state response, the steady state means a final value, okay? So you can put the sign of equal, okay? That means the final value in control theory means what? Steady state. That's it. All right. So if we know the function in frequency domain, you calculate this term, then result will be the final value in time domain or steady state response of output or steady state response of error. All right. So this result is very, very useful in control theory. Okay. So that's the first benefit of making use of a Laplace transform. So it means we can reduce the complexity of equation in time domain and transform such a complexity of equation in time domain into simplicity of equation in frequency domain. All right. Then second benefit will be this transfer function, because in time domain, we can never define transfer function. To be remembered, transfer function is a unique feature in frequency domain. Okay, so that is the second benefit for us to work in frequency domain. Then what is a transfer function? How come we discover this transfer function? The reason is because in time domain, output is equal to the convolution between input and the relationship function. Then you will see this is a big headache for us to do integration with multiplication of a two-time function, right? However, with Laplace transform, then we discover output, Laplace transform of output is equal to Laplace transform of input times Laplace transform of the relationship function. Then you see the GS actually is a ratio between YS over XX. Therefore, such a simplicity and make us to pay attention to this function in time domain or in frequency domain. And we call this function GS as a transfer function. All right. So that is the definition of a transfer function. Transfer function basically means the ratio between Laplace transform of output and the Laplace transform of the input. So then application of a transfer function is to transform input signal to output signal by doing multiplication. Okay, so all these occur in frequency domain, but not in time domain. All right, so this is a extremely useful result. Okay. Then based on this result, then the sub-benefit will be the graphic display of an inner structure of a control system based on use of a transfer function. Okay, before we look at the definition of a block diagram, then we just take a look of application of a transfer function to the motor. Okay, so here you see we have a motor and you drive a payload in magnetic domain. So you can imagine our robotic arm with a 6 degree of freedom. Actually, the complexity is equal to 6 times this one. If you understand the dynamic behavior of this motor, actually you understand the dynamic behavior of your robotic arm already. All right. Okay. So you treat this flywheel as a generalized payload. This may correspond to the link of your arm. Then on top of the link, you may have other link, etc. Okay, you lump them together. Then you have this equivalent payload, and we name it as a flywheel. Okay, and we know the moment of inertia equal to this one. All right, because the shaft of the motor is always supported by bearing, then there's a visco friction. If we know the damping coefficient, therefore we know the resistive force. Okay. So this question asks you to establish the transfer function. Assume this is the motor drives the wheel of a mobile base, because the output in this case is angular velocity. Omega is angular velocity. Okay, then this corresponds to the situation you drive your mobile base, then the wheel keep running. All right, but pay attention for robotic arm inside. Usually by default, the motor will undergo position control. You move, you do the pick and the place. That means you move from one angle and to reach another angular position. Okay, so then this is relevant to the motor inside the mobile base. Okay, so then we also ask you to to determine time function, okay, of velocity, and without using the inverse Laplace transform. So we will show you a technique which is called as a partial fraction expansion. So the principle is extremely simple. So I just show you through the example. Then you will see, okay, actually, once you have a frequency domain function, it's quite straightforward for you to know what should be the time domain function. All right. Okay. So first, we have this payload. Then motor will supply this torque. This is magnetic energy. Then this magnetic energy will overcome visco friction. Visco friction is proportional to angular velocity. So it's further order derivative of shaft. Then remaining energy will contribute to the acceleration by the magnetic payload, okay, with this moment of inertia. All right. So here we are interested in velocity. Therefore, this is omega. Then this is omega dot. Then you see you have a simple differential equation. You still have derivatives here. Then in order to reduce complexity, we apply Laplace transform. Then in frequency domain, this becomes S times Laplace transform of omega plus B times Laplace transform of omega equal to Laplace transform of top. Okay. Then we can compute ratio between omega S and the TS. Then result will be like this. Then this is a transfer function. So you see, very simple, John. So denominator is a polynomial equation of S of a degree 1. All right. So now if let's say we apply a constant torque, okay, then the motor output a constant torque. It's like your mobile base on the go uniform motion with a constant velocity. Okay, then in this case, what should be the time function for the angular velocity? Okay, so since the ratio between output and the input is equal to transfer function, therefore you know Laplace transform of omega equal to transfer function times Laplace transform of input TS. Since we know the torque function in time domain, then Laplace transform is equal to 1 over S times 100 because the torque is equal to 100 Newton meter. All right. So this means a Newton meter, it's not the M minus N, Newton meter. So this is a unit of a measurement for torque. All right. So in frequency domain, you have 100 divided by S. Therefore, Laplace transform of angular velocity equal to transfer function times 100 over S. Both sides we cancel out the 100, then we have a 1 over S times 1 over S plus 0.1. Then this, we do a partial fraction expansion because we have a two root. Then this is equal to the sum of these two terms with the coefficient A plus B divided by this. Assume you do not know what is A. Then both sides times the denominator below A, in this case is S. Both sides times S. Then S will cancel out that. Then here you have an S. Then we let the S equal to 0, then this disappear. Then here you only have an A. Then when S equal to 0, then here is 1 over 0.1. Then A equal to 10, done already. Then here assume this is a B, okay? Then both sides times denominator below B. So in this case, it's S plus 0.1. Then here you have a S plus 0.1 times 10. Here you have a 1 over S because S plus 0.1 cancel out that. Now we let the S equal to negative 0.1. Then this becomes a 0. Then you only have a B here. So here you have a S, you have a 1 over S. When S equal to negative 0.1, then it's 1 over negative 0.1. Then result is what? Negative 10. So this is a way for you to determine A and the B. Okay, partial fraction expansion means if you have a two root, then this is equal to the sum of two terms. One is with this root, second one is with this root. All right. If you have a three root, then this is equal to the sum of a three term. Okay, each term corresponds to each root. Then in the numerator, you have a coefficient A, B, C. Then you apply the same method to determine A, then determine B, then determine C. All right, okay. So once you have this simple Laplace transform, then you see 1 over S in time domain is what? Is 1. Then 1 over S in time domain is 1. but this S will undergo a shift. Okay, once you undergo your shift, then in time domain is equal to 1 times natural exponential function raised to the power, which is equal to negative 0.1 t. Okay, because this is a shift, which is equal to negative 0.1. Then it's a negative 0.1 t. Done already. Okay, then you can estimate what should be the steady state response of this omega. So when t go to infinity, then this becomes 0. Then you see this will be the steady state response of velocity. Okay, so you see Laplace transform is very, very powerful for us to handle to study the dynamic of a control system. All right. Okay. So here we show you the forward open loop Laplace transform. Then how's about the transfer function? Okay, with a closed loop control system. For example, let's say we construct this negative feedback. Okay, then in this case, what should be the equivalent transfer function between output and the input? Then this will be the first formula in control theory. This is like a Newton's second law, you must remember when you study physics. Okay, so this formula tells you the equivalent transfer function is equal to forward branch 1 minus a loop transfer function. All right, so I guess we have encountered application of this formula in lecture 1. Okay, now you see. Okay, so we explicitly describe this formula. Okay, in control theory. So this is something you need to remember. Okay, when you have the background knowledge about the control theory, it's like when you tell people you know physics, then you must know what is Newton's second law. Okay. And this is similar. If you tell people you understand control theory, you must know this formula. All right. Okay. So that is the benefit of using Laplace transform, because based on the use of Laplace transform, then you can have this transfer function, which is equal to the ratio between Laplace transform of the output and the Laplace transform of the input. Then the next benefit is to use transfer function to visualize the inner structure of a system under control. Okay, then actually when you see this diagram, this is already block diagram already. Okay, so now we give you a formal definition. What is a block diagram? Block diagram basically refer to the signal flow in frequency domain, or flow of a Laplace transform in frequency domain. Okay, so which are interconnect together. Okay, so this is the nature of a block diagram. All right, so with the block diagram, then we can visualize a very complicated control system. For example, here we have a control system, and if we draw out the block diagram, draw out the signal flow in frequency domain, then results like this. Okay, then the next benefit with block diagram is what? Is the simplicity in reducing a very complicated block diagram into a simple one without solving any equation. That is the beauty with Laplace transform and the transfer function. You see, if you are going to write down the equation which relay all the signal together inside this block diagram, you will have a lot of equations. Then you must solve all these equations to find out the solution of CS in terms of RS. Immediately you can imagine this is a very complicated task in mathematics. However, with block diagram, you will see the beauty. We can reduce this one into a single transfer function without solving any equation. Okay, so I use this example to illustrate to you the procedure. Then you understand the power of making use of a Laplace transform and making use of a transfer function, making use of a block diagram in frequency domain. Okay, so first we can modify this local structure. This is a summation, just add these two signals together. This is summation. Because we can change the structure as long as the relationship among the signal remain unchanged, okay? Because the easiest way to change summation is because if let's say you do A plus B is also equal to B plus A, China. Or A plus B plus C is also equal to C plus A plus B, yes or no? So it means what? The sequence, the order of doing summation does not matter. Understand? A plus B plus C equal to C plus A plus B. That's it. So you can swap these two. Then, okay, we do the swap. Then switch 3, summation 3 come first, followed by summation 2. Then you see summation 3 come first, followed by summation 2. Now, then this control structure looks better. Okay. Now here you see this control loop does not look like this control loop because for you to apply this formula, you must make sure there's no signal come out. The structure must be perfectly like this. Then you can apply this formula. All right. So then here you see there's a signal come out. Okay. So this means what? This module will take this signal as an input, but this signal will appear in the downstream because if this is X, then here is what? X divided by G2. If I pick up a downstream signal, then I restore it back to the upstream signal, then nothing changed. So I pick up this signal divided by G2, then I will restore original input signal. So therefore, I can shift this one to here. Instead of picking up upstream signal, I take this version in the downstream. Okay, so you shift this one downstream. Then I divide this signal by G2. Then I can restore original input signal because the downstream version is equal to upstream version times G2. If I divide by G2, then I restore original input signal. Okay. Now the good news is what? This is the sender negative feedback loop. Okay. Then we can apply the first formula in control theory to replace it by the equivalent transfer function. Okay. So then the equivalent transfer function is equal to forward branch transfer function 1 minus loop transfer function. Forward branch divided by 1 minus loop. Okay, you get this one. Then what is this? This means is the parallel contribution from this signal to the same downstream signal. Then parallel contribution means what? You add them together. So this is equivalent, you have a 1 here. Okay, all right. Then this become a 1 plus H1 divided by G2. Now you look at this. This is the standard negative feedback control loop. Then you replace it by the equivalent transfer function. Forward branch divided by 1 minus loop. Forward branch divided by 1 minus loop. Simplify it, you get this one. Then here. Now for this loop, again, you can replace it by the equivalent transfer function. Then result is a forward branch 1 minus loop transfer function. Simplify it, you get this. Further simplify, you get this. Finally, you get this result. You see, we never solve any equation. Then we obtain final transfer function between CS and the RS. So it's magic, China. So then you see the beauty of making use of block diagram. Okay, and this result is possible only with the use of a transfer function and the Laplace transform. All right. Okay, now we try to apply all this benefit to help us to understand our robot's inner control structure. All right. Okay. So we are going to do this. And first of all, if we have a robotic arm with 6 motor, then you understand we have a 6 link joint and the 6 torque joint and the power joint, etc. Then for the controller, we must have a 6-axis controller. That means the controller can control 6 motor in parallel. We must also have a set of 6 power amplifier. Therefore, immediately you understand for robotic arm, we face MIMO system. Okay, so this is very difficult for us to study or play with MIMO system. You remember there is a property for LTI system. If we have an LTI system, then MIMO become sum of SISO. Therefore, our target is to see under what condition the MIMO system of a robotic arm could become a sum of a SISO system. That is a target for us to, to move into, all right? So before we can reach that target, then we need to draw the block diagram. Then by looking at the block diagram, then we see how to meet the condition. Okay, what should be the condition for us to impose in order to make this robotic arm to behave like a LTI system, all right? Okay, so we start with this result. This is a result that we have a study in lecture 2. So I hope you remember. Then here you see you have a double dot, then you have a top, then you have a D term, Inside here you also have a double dot, single dot, etc. Okay, so what we do is we apply Laplace transform, then double dot become a S squared, then Laplace transform of a QM. Here is Laplace transform of a tau, Laplace transform of a ds. If we compute Laplace transform of a dt, then here you have a double dot, then become S squared. Here you have a single dot, then you have a S. And here, actually you have a G function and QM. So this conceptually, you can write it at this way, okay? So that means this will, depends on the Laplace transform of a QMS and also Laplace transform of a TS, right? So just conceptually, we follow this notation because we do not need to know the exact expression, because later on you will see, okay, this will disappear, right? Okay, then both sides divide by S squared, because okay, we have S squared here. Then QMS equal to 1 over S squared, okay, times this one. Then ds is equal to this one, okay. From here, then we can start to draw the block diagram, okay. First, we have this signal in frequency domain is the top. Then we have this D signal in frequency domain is the ds. So this is a subtraction. Then we use this summation device, okay. So this one times positive one, this one will times negative one. So this meaning then becomes subtraction. If this is positive, then this one times this one plus this one times this one, then it becomes additional. If it's negative, then it's a subtraction. Then the output will be this signal. So it's a tau S minus ds. Then pass through this transfer function. Now you see this is a transfer function. Then we reach here. Then this signal must times 1 over S times 1 over S. Then we get this signal. This signal must again times 1 over S. Okay. Why we split it into 2 1 over S? So you remember 1 over S corresponds to integration in time domain. Okay. If this is a position, then what will be the signal? Physical meaning of this signal here is velocity. If this is a velocity, what will be the physical meaning of the signal here? This will be acceleration, all right? So then it means signal from here is a position, signal from here is a velocity, signal from here is acceleration. Then you look at the D. D equal to this transfer function times this is what acceleration. So then you have a transfer function times acceleration, give you the first term of a ds. What is this? This is a transfer function times velocity. Velocity, you can take it out from here, okay? Then you get the second term. Then this one, you will take the input from position. Then you have this transfer function, so you put inside, this is a transfer function. Then add them together, okay? This is summation, summation, all positive, positive. Then you get the ds, then ds will be here. So then this is the block diagram for this function, okay? So this is the block diagram. So this block diagram show you with the input of a tau at the shaft of the motor. Then you will see position signal at the shaft of the motor, okay? Then if let's say we treat it as a black box, then actually we can also output velocity, output the acceleration, treat this as a black box. Then input is a top, output will be position, velocity, acceleration. But if you want to zoom in into the inner structure, then this will be the answer. Okay, now you see clearly what will be the inner structure. Okay, here you just need to pay attention here. You see this is the inverse of speed reduction ratio matrix. another inverse of speed reduction ratio matrix. Then you can ask yourself, what happens if this, I just pick up one value. If one speed reduction ratio is equal to 500, then 1 over 500 times 1 over 500 is what? 1 over 250,000. 1 over 2,050, 1 over 250,000 is a very, very small number. Then you can start to imagine how to make this guy disappear. To choose speed reduction ratio to be reasonably large enough. That's it. All right. So then you will make the robotic arm to behave like the LTI system. So that is magic in industrial robotics. All right. So this is a very, very important discovery. Okay. Or information or knowledge about the design of a robotic arm. All right. Now we move on to look at the block diagram at the power joint. So this is a dynamic differential function in time domain, which relay control signal from robot brain to the mechanical energy at the input of torque joint. Okay. So then what should be the block diagram? First, you see we have a first order derivative here, first order derivative here. Then we do Laplace transform. Then this first order derivatives will become S times tau m. This will become S times Qm. Then all the rest are coefficient. Okay. So since we have a lot of S the coefficient, so you must pay attention. Okay. So you focus your attention on the signal in frequency domain, this one. And this is signal about the torque. Then behind this signal, we have the mechanical energy. Okay, then this one. All right. So then we continue. So what we do is we merge these two together because here you have a tau ms, you have another tau ms. Okay, and pay attention. I here means you have n such a motor or controller or power amplifier, I equal to 1, 2, 3, all the way to n. For normal robotic arm, n equal to 6. If let's say your robotic arm with a 6 degree of freedom, then n equal to 6. All right. So you add these two together, then you see this is a coefficient in front of tau m plus second term. So you have a first term, second term. Okay. Then we continue from this one. Then we shift this toward the left-hand side, okay? Because later on we will compute inverse of this one because we want to express the output as a function of the input, because this is the input to the robotic arm, because this is output from robot's brain. Then this will produce this output toward the robotic arm. So we want to express the output as a function of the input, okay? So this is the input to the body. It is output from the brain. Output from the brain will become an input to the robot body. All right. So then we shift this to here. Then we have this. Now we define a simple coefficient because if we write this complex coefficient, then waste our time. Okay. So we name this as a Ke. We name this as a 1 over Km. We name this as a Tm. Okay. Then we have this simple expression. So again, we can also simplify this, name this as a 1 over another transfer function, okay, to make the notation even simpler. Okay, so we name this one as a 1 over Gs. Then Gms will appear toward the right-hand side, okay, shift it to here, then swap the equality. Then we can express output, okay, inside the robotic arm is a function of the input to the body, to the robot's body. All right. So once we have this, then we can draw, okay. Or before we draw, we can, okay, combine all these n equation together, write them in the matrix form, okay. Because here this is a scalar, this is a scalar, and this is a scalar, this is a scalar, this is a scalar. So then we define this vector, we define this diagonal matrix. Then we continue to define this diagonal matrix, put this into a vector, define this as a vector. Then this is a system of n equation, will become a single equation in matrix form. Therefore, with this one, then we can easily draw this block diagram. So you see this vector minus this vector. So this vector minus this one times KE. So then become this vector. Then output times this transfer function will give us the signal about the tau m. So then this is a block diagram at the power joint. Okay. Now we have these two. Then the question is, can we combine these two together? So you look at the carefully about the nature of the signal. From the brain of a robot, we issue this signal, and this signal will produce this mechanical energy inside the body of the robot. Then if the robot receives this energy, then robot will output this motion in terms of position, velocity, acceleration. Because this one are the same, then you can link them together. So you put them together, you see the nature of these two are the same. So we can link them together. In addition, because for this block diagram, we need the input from velocity. Then here you see this block diagram will output velocity. So we can take the signal from here, then supply it to here. Therefore, the final block diagram for robots dynamics under control is like this. So you see, this is a signal come from robot brain. Then this is a behavior of your robotic arm in terms of position, velocity, and acceleration. Okay. So next question, how to make this become a LTI system? So you start to think, okay, because this is a MIMO system, because this is a vector, all these are vector. Okay. So when we face MIMO system, so it's always good to make it to become a LTI system, because with LTI system, then MIMO become a sum of a SISO. Okay, so in lecture 4, we will show you the condition for this one to become a LTI system. Okay, so that's all for today's lecture, which is about lecture 3. Okay, so the key takeaway from lecture 3 is for you to have a quick study about the important property of Laplace transform, and therefore, immediately you see the two important benefits with the Laplace transform. One is to have this definition of a transfer function, and the second one is the ability to make use of a transfer function to draw the inner structure of a system under control. Then the last key takeaway from today's lecture is to apply the concept of block diagram to visualize the inner control structure of a robotic arm. All right, so then this is the result of graphic representation of dynamics under control with robotic arm. Okay, then in lecture 4, we are going to see how to make a nonlinear system of a robotic arm to become LTI system. All right, thank you for your attention, and I'm looking forward to seeing you in the study of lecture 4.